So welcome to the course Concurrent Algorithms and Data Structure for this year, 2024. So the course will be mainly given online. And my name is Parosh, and I'm the responsible teacher for the course. And to my help, I have two course assistants, namely Fritjof and Tage, whose emails are written here. And of course, you are all the time welcome to contact us if you need help, whether you come to our offices and email through Studium or through coming to the lectures where we will be available. Although the course is given online, we will be available from time to time physically in the classroom to answer questions, as I will explain later. Okay, so first, an outline of the course. First, the examination of the course. It consists of two parts, namely a set of assignments and a written exam. Now, the assignments, we will have two types of assignments, theoretical ones, 3 of them, and programming assignments, 3 of them. Now, if you look at the assignments, they should be solved individually by each student separately. Of course, we encourage you are allowed, and in fact, you are encouraged to collaborate and discuss the solutions of the assignments, but please try to do them by yourselves. So if you look at the programming assignments, they are mandatory and they have to be turned in before the respective deadline. For the theoretical assignments, they are not mandatory, but they are strongly recommended. And the reason is that, from experience, I know that they will help you immensely with the exam, where the questions will be quite similar to the ones that you have to solve in these assignments. And this will help you ultimately to achieve the main goal, which is to understand and master the concepts that we will cover in the course. So to pass the course, you have to pass the written exam, which will be given at the end of the course, and to pass all the 3 programming assignments. Now, there is also a bonus system for the theoretical assignments. This is one more reason to do the theoretical assignments, because each one of them, if done well and turned in before the deadline, it will give you up to 3% score in the final exam. So this means that if you do all 3 theoretical assignments and do them well, get good scores, then you can get up to almost 10% score in the final exam. So on the one hand, they will help you to understand the course content, and they will simplify your task in passing the exam or getting good score in the exam. And also they will help you in the exam through the bonus system, because 10% can be the difference between failing or passing, or getting a score of 5 or 4, etc. So in conclusion, the programming assignments are mandatory. The theoretical assignments are not, but you are strongly recommended to do them. Okay, so as I said, this will be an online course, mainly through videos. And this is the second time I do this. The first time was during the pandemic. Anyway, as usual, the course contents and all the information that you need about the course will still be available in the Studium platform, as you might already have observed. And there I will send frequent announcements concerning different things related to the course, assignments, solutions, new videos, etc. You will find all the course information, the slides, the course literature, reading lists, assignment results. The assignment themselves will be put there, and the solutions, etc. For the video part, there are different parts. So first you have the main videos. These are already available on YouTube, And some videos will be available on Studium. We will see. So the main videos are the main lectures of the course. But throughout the course, I will also provide a sequence of short videos, like this one here, or not this one here, in fact, but I will, because I will integrate this into some other video. So this one, no, it's not a short video, but I will provide a set of short videos with extra information like updates to the existing videos, corrections, but also more importantly, perhaps, to provide I will provide a lot of exercises, and I will present their solutions in terms of short videos. And the same applies, for instance, to the assignments, the solutions to the assignments and all exams. So all these things I will provide slides, and then I will explain them through videos that I will announce through the Studium system, and I will put them on YouTube, either on YouTube or on Studium, or both. Okay, so because it's an online course, it's very important with interaction between us teachers and you students. So, and to that end, I will physically attend some of the lectures, and I will use the given lecture slots according to the official course schedule, so that it does not collide with other courses that you might be taking. And the purpose is that to discuss the videos, have discussions, and answer questions in case you have any around the videos and the other content or the other parts of the course. If needed, I can provide also Zoom sessions, and then I will announce the times when I will be in the lecture room physically, or if I plan to have a Zoom session, then I will, of course, announce them beforehand, at least 2 or 3 days before. And one important thing in the interaction is that if you have any questions, then you should send them beforehand. And the reason is that I can prepare. You don't need to do that, but if you can do that, if possible, I think it's better. And also because, more importantly, I will try to provide answers globally if relevant. For instance, if somebody is asking about an algorithm and there is an aspect that I would like to explain more, then I will do that and record a video and put it online again. So the technical question answers will be through slides that I'll put on Studium, but also through in some cases through videos that again I put on the Studium platform, or maybe both on Studium and YouTube. Okay, so the course literature is this book, The Art of Multiprocessor Programming. This is a classical book on multiprocessor programming, and parts of it cover the course by Herley and Shavit. These are well-known researchers in the area. And in Studium, I provide a reading list to which parts of the book are relevant. So, and we are in the internet era, so for some parts of the course, I'll refer you to the internet. But more or less, the course will be, and the lectures are self-contained. So, in fact, by watching the videos and if needed, coming to the classroom, then I think you will acquire quite a lot of knowledge. Certainly enough to do well in the exam and pass the course. So still, we should not forget Studium. This will be the main interface, as usual, between the teachers and the students. So as I told you, I will provide course information, slides, assignments, results, evaluations, course evaluations, and now even videos, etc. And one thing which I have observed before is that some of these files, the slide files, can be quite large, especially the ones that are in Keynote, because I'll provide different versions, or 3 versions at least: the Keynote files, PDF, versions, and also low resolution PDF versions. But in any case, try to download the slides first before you go through them, because some people try to watch the slides online, and this can be difficult. So download it to your hard disk and then run the animations after that. Okay, so let's start with the course. So the outline of the course. So today I will start with an overview of the contents of the course, the motivation, the basic problems that we are going to look at. And then, as I told you, we will consider basic data types or basic data structures and the associated algorithms. And we will recall them from the sequential setting, from the setting of sequential programs, and try to extend them to the concurrent setting. And as I told you, this will not be trivial. In fact, even to know what it means for a data structure to be correct in the presence of concurrency is not trivial. To make things more systematic, I will introduce a concept which is called abstract data types. So it's a fancy name, but in principle, at this level, just a way to describe these basic data structures like sets, queues, and stacks in a uniform manner. And in particular, to be able to talk them uniformly, both in the sequential and the context settings. I mean, this is a formal theory, which I will not go through in this course. This is not the subject of the course. I will just give you a hint of the main ideas and the flavor of abstract data types and how they can be used to formalize data structures. And this will be done in a very lightweight manner. So you don't need any formal knowledge of language theory or abstract data types for this. And then we will instantiate this framework of abstract data types in the context of sequential programs, just to recall some of the things that you already know from sequential programs, and so that we start talking the same language, if you wish. Because some concepts which are kind of trivial in the case of sequential programs become rather non-trivial when you have concurrent programs. So what we will do is that we now, after doing sequential programs, we will go to concurrent programs and see what the differences will be. And first, we will define the notion of correctness. What does it mean for a concurrent algorithm to be correct? And for that, we use the abstract data types, and then we start going through algorithms, different algorithms for the manipulation of data structures like sets, queues, and stacks. So first, we will start with set algorithms, and we define different methodologies to manipulate data structures. First, we will only instantiate them for sets to make things, to keep things as simple as possible. So we look at different strategies to implement data structures, like coarse-grained locking, for instance, fine-grained locking, lazy lists, optimistic lists. So all these things we will instantiate as set algorithms, and then we try to explain what happens if you try to instantiate them for sets, for queues and stacks, for instance. And concretely, we will look at stack algorithms like the classical Treiber stack algorithm or the so-called Michael and Scott queue algorithm. Time permitting, I will go through some other topics like transactional memories and weak memory models and things like that. But these are the basics that I would like you to learn from this course. To look again at basic data structures, to recall sequential programs and see what will happen when you go over to concurrent programs. And in particular, what it means to be correct in that setting, to design different algorithms, to compare them from the point of view of correctness, complexity, and efficiency, and to instantiate them to concrete data structures such as sets, queues, and stacks. So any questions up to now? So let me see whether I can open the chat. It says recording in the corner, so I think it's working. Very good, very good. Thank you very much. I only look at the
Linus. So I only look at the chat window from time to time. If you have any questions up to now, please ask now. And as I told you, if you don't want to ask now, you can ask me later. Also send me email and I will answer in the next lecture. But you are welcome to ask now also. So now the outline, the overview. So this is the outline of the course, overview, and which will be the subject of the lecture today. Overview, we will go through algorithms and data structures. We will look at concurrency, efficiency and correctness, and then I'll introduce some concepts that we will use, namely specifications, safety properties, and liveness properties. So let's look at algorithms and data structures. What they are, we know what they are. At least we think we know what they are. What happens when you have concurrency? So algorithms and data structures. So algorithmics. Well, I mean, it's easy to get the impression that algorithms were invented due to the introduction of computers, but this is far from being true. In fact, algorithmics is an old science, one of the oldest sciences, if you wish. You can find classical algorithms already from the time of the ancient Greeks. For instance, this is a classical algorithm that's still taught in undergraduate courses, the GCD algorithm, finding the greatest common divisor of two integers, which was invented by Euclides. So this is a few centuries ago. And you can find more about this algorithm if you don't know it from the internet. But most people do know it. We teach it in the basic courses on algorithms and data structures. The classical algorithm to approximate the pi constant was invented by Archimedes. So these are quite impressive and elegant algorithms that were invented many, many years ago. So algorithms is not something, they are not something which are new. Here you can find a description of this approximation algorithm for the pi, which was, it's quite old. So what's new with the algorithms then? Well, the new thing is that now, since the introduction of computers, we have a tool that can, in which we can run our algorithms quickly, efficiently. So you can run the GCD algorithm for a couple of integers like 10 and 15. It's not very difficult, but if you have big numbers, then you get trouble. So the thing with computers is that we can mechanically execute algorithms as programs. So once you have an algorithm nowadays, you can implement it as a program. And then once you have a program, you can run it on a computer system in general. Because for me, a computer is a general concept. It can be a piece of hardware. It can be a program. It can be a distributed system. So the new aspect of algorithmics is they can be encoded as programs which computers understand, and therefore we can run them efficiently. In fact, I would claim that algorithms are the basis of computer science. This is true both at the hardware and the software levels. I mean, even if you look at hardware, if you look at modern microprocessors, for instance, if you look at the ARM processor or the IBM Power processors, or Intel TSO or x86 processors, all these are modern processors which can implement complicated algorithms whose goals is to gain efficiency and save power. So already at the level of hardware, you see a lot of difficult algorithms. Needless to say, software is concretization of algorithms or algorithmics. So, I mean, if you take any program, it is based on an algorithm which has been encoded as a program, piece of software which you can run on your hardware, which is the computer. So again, algorithmics is an old science, but due to the invention of computers, now we have the tools to run them efficiently. And of course, this has resulted in a substantial effort to develop new algorithms which can be run efficiently on computers. So this is a science in itself. And in fact, inside the subject of algorithmics, there are numerous sub-subjects specializing in different aspects of algorithmics. The design of different algorithms for new applications, the analysis of algorithms from the point of view of correctness, from the point of view of time efficiency, space efficiency, etc. So the invention of computers allowed us to take advantage of the elegance and usefulness of algorithms. It opened the door to design new algorithms, but on the other hand, it also defined new challenges that have been undertaken by the computer science community during the last 5 or 6 decades, or even more. And now we are facing new challenges due to the introduction of concurrent systems, in fact. Okay, so we go back to basic algorithms and data structures, as I told you. In this course, we only look at basic algorithms and data structures because they are sufficiently difficult to cover in a course and sufficiently interesting to give you a flavor non-trivial to give you a flavor of the challenges that arise due to the introduction of concurrency. So in fact, these two concepts, algorithms and data structures, are intimately related. Because if you have a data structure, you need to manipulate it using algorithms. I mean, a stack is just a data structure, which is a linked list, but I need a simple algorithm that allows me to push and pop elements to the stack. Also, you cannot possibly implement algorithms efficiently without the use of efficient data structures. And if this, of course, you know, if you have written any programs. So these two concepts are intimately related, and one of them is needed for the other. So you cannot, in fact, it's very hard to separate these two issues, the design of algorithms and data structures. And this is something that we look at. So therefore, we consider both algorithms and data structures, but now in the concurrent setting. Right, so let's take a simple example, that of a stack. So what's a stack? Well, I see a stack as a data store, as a data structure that stores some values, something like this. In fact, the concept of a stack is quite deep because although it is deceivingly simple, it is of great importance because it allows you, for instance, to implement recursion. Recursive calls are put on a stack, and when you return a recursive call, then you pop from the stack. So when you make a recursive call, you push something to the stack. When you return from a recursive call, then you pop that call from the stack. So it's a fundamental data structure, but it's very simple. In fact, what you do is that you have the concept of the top of the stack. So you always operate on the top of the stack. And you operate on the stack using two operations as usual, the push and the pop. So push, suppose that we have a stack in which we put integers. So then I can have an operation which tells me push 3. So this means that I take the top of the stack and I push a 3 to the top of the stack. And what it means in this case, because the stack is initially empty, when I do the push 3, I just put the add element to the top of the stack. So I create the 3, and then I push it to the top of the stack, and now this will be the topmost element of the stack, the 3. Now you can push a 5, and the same thing happens. I take the top of the stack, I create the 5, and push it to the top of the stack. So always I am working with the top of the stack. And then I can do a push 4, for instance, and the same thing happens. I push the 4 and put it on the top of the stack. So always when you push elements in the stack, you put it at the top of the stack. It's easy to implement such a stack using a linked list by just keeping track of the cell which is the top of the stack. And then if you have a new element which you want to push to the stack, you just put it at the position where the current pointer to the top of the stack is. If you do a pop, then the only thing you can do with a pop is to pop the topmost element in the stack. So you remove and fetch, and remove the topmost element from the top of the stack. So the 4 will disappear. So easy enough. This is the stack as we know it from our first programming courses. And it's very easy, almost trivial. And sometimes we call it last in, first out data structure, which means that the last element you put inside the stack is the first one you pop. This is just a name that's used as an alternative to the one of the stack. Now, what happens if you consider concurrency? In fact, I can tell you even this innocent data structure, which is the stack, turns out to be enormously complicated. And the basic reason is that if you have concurrency, you will have concurrent processes by definition. You will have concurrent threads. And these threads operate in parallel, which means that, for instance, maybe 2 threads will do push operations at the same time. So it's not clear which one of them will go first. So we say that there will be collisions. So in the concurrent setting, there will be collisions. And this is simple to define, but it has very severe consequences, making algorithms that are both efficient and correct quite complicated, as we will see in the course. But first of all, why bother about algorithms in the presence of concurrency in the first place? We know our algorithms from the sequential setting. Why bother about concurrent systems and make life difficult for ourselves? Well, there is a motivation for that. And the simple answer is that concurrent systems are nowadays everywhere. Sorry, drinking some water. So this means that as a computer scientist, you are supposed to know what will happen in concurrent systems when you have concurrency. And the first thing you need to know is that what happens to the basics. And this is what we are doing in this course. We go back to the basics. So why are concurrent systems everywhere? Well, because you find them at all levels of system design. So if you take the lowest level of system design, if you take any course on computer architecture, nowadays, they will tell you that you have multi-core architectures. In fact, there are single-core architectures or single-core processors are not found anymore. And this has to do with physical phenomena. In fact, there is something which is called Moore's law, in which we say that we get free lunch. Free lunch, the meaning of that was that by just making your processor more efficient or increase the speed of your microprocessor, you would increase the speed of your program without doing anything. So if I implement something now, in 1 year, I could buy a processor which was twice as fast as the processor that I have now. So I could just observe that my program was suddenly twice as fast as before, although I had not done anything. And this was what was called the free lunch. But this was over a few years ago because there were some physical limitations on due to energy consumption, for instance, and the generation of heat. There were some physical limitations on how quick or how efficient your processors could be designed. Therefore, instead of making the processor more quicker, the idea is now to put several cores or to have a multi-core architecture in which several cores operate in parallel. And here is where the source of efficiency is. By dividing the tasks and distributing them on the processors, you will get more efficiency. And therefore, the current architectures are all multi-core. Of course, this introduces a lot of complications, but these are not the subject of our course here. But what we need to know is that if you take any processor by the leading manufacturers, Intel, ARM, IBM. If you look at their processors, they are all multi-core, in fact, which consequently means that if you take any computer, phone, or complicated computer system, then almost certainly you will have a hardware which is multi-core. And in particular, this means that on these multi-cores, you have threads that operate in parallel. So you do have concurrency at this low level of system design, at the level of a chip. But this is not restricted to the architecture. In fact, if you take the highest possible level of system design in distributed databases or distributed systems, they are also implemented in a concurrent way. I mean, this is true for databases used, for instance, by Amazon, by Facebook. And the idea there is that you have what we call geo-replicated systems. So although this is hidden from the users, if you look at the implementation of the Amazon or the Facebook database, you see that you have servers that are distributed around the world. And as a user, if you are in Sweden and try to interact with such a node, it's very short. So you do not realize that you have this geo-replicated data system. You get what seems to be an atomic interaction with the system. But in reality, what happens is that all these nodes will communicate together. And the goal is that to have a coherent, uniform picture of the state of the database around the world, regardless of where you are. So if you see a message in Facebook in Sweden, the other users should see the same message in the United States or in Asia or anywhere in the world. And this is not easy. In fact, the study of distributed databases and geo-replicated systems is a hot topic of research nowadays. And what I want to tell you here is that concurrency is everywhere. So you have at the architecture level, you have at the distributed system level, and in fact, this is also reflected in programming languages. So if you look at the latest definition of C++ or Java, of any such language, you see that you have parallelism and concurrency inside the language. And then you can talk about things like threads, tasks, locks, relaxed accesses, sequential accesses, acquire and release. Again, these are things that, in fact, we study quite intensively in our research, but these are not the subject of the course, just to put it in a context. What I would like to tell you is that concurrent systems are everywhere, and therefore, if you take a job in the future, most probably you need to deal with concurrency in some shape or form. So this is the motivation for concurrency. Now I will check whether there are any questions. So let me see. A chat. I didn't took the course of Costis. Can I survive this course? Yes, you can. You can survive this course without having that course. So as I told you, I will try to make the course self-content, and whenever I need some concept which is not easy, I will try to explain it. And if you don't understand, please ask me. This is the best way. So I will not have anything complicated that you need from other courses. And this is usually my style. This is a challenge that I undertake to make the course self-content. And rather than going into details, I'll try to give you some main concepts to motivate the concepts and to tell you why it's interesting and why it's difficult. So the combination of difficulty and interest is a nice combination that we should all like. Any questions up to now? No? Okay, don't be hesitant, just ask questions. This is the first time for me I do this online, so it is interesting for me too. You are more experienced, I assume that you have taken such courses before, but you are welcome to ask questions and you are welcome to send me mails. I will try to answer all your questions. Of course, I may not know how to answer, but I'll do my best. Okay, so this was the motivation for studying concurrency. Let me see what the time is. So I have turned off my phone, of course. Okay. So now oh no. So this was the motivation for introducing concurrency. Why? It's not that we want to make our lives difficult just because we like to make our lives difficult. It is because concurrency is here and we need to deal with it. And mostly we don't know how to deal with it. But for the basic things we know, at least we think we know how to deal with it. So let's see why it becomes difficult now. Let's go back to our example of a stack. And this is a picture that I will use quite a lot, these screws. I mean, because they have threads, and I like woodworking, so I started doing woodworking a few years ago. So for me, when I say thread, I think about these threads. And therefore, I decided to illustrate threads in this course by using screws. And by the way, I have drawn all these in LaTeX, so which is something I'm quite proud of. I have a macro, which as a parameter, I can give the color, the number of threads, the thickness of the screw, and the length. So this is wanting to make life difficult just for the sake of it, but sometimes it's nice to do that too. Anyway, so let's go back to the example of a stack and the overview here. The goal of the course is to go to the concurrent setting, to reconsider basic algorithms and data structures, but now in the concurrent setting. As an illustration, let's go back to a stack. Now, suddenly, instead of one thread, we may have two threads. Usually, you have thousands of threads. And suppose that these two threads, they are trying to do two push operations simultaneously. And in reality, as we will explain later, these push operations are not atomic operations. I mean, in the sequential setting, you can assume it's atomic, because if you have a program which does a push operation, well, it will wait until the push operation has been performed before proceeding to execute the next instruction. This is by the very nature of sequentiality. While in the concurrent setting, as you will see later, these operations may overlap. So now we have two push operations happening in parallel, and one of them tries to push a 4 and the other one will try to push a 7. So the question is, which one will take effect first? So in this particular example, maybe the 4 goes first and then the 7. And in such a case, we say that thread 1 goes before thread 2. So first of all, there is something to be defined later, which is goes first, takes effect. What does it mean to take effect? So this we have to define, but for the sake of this example, we say that takes effect means that you perform the operation. So in this particular scenario, for some reason, we decided that the green thread, thread number 1, goes before the red thread, which is thread number 2. But you can also imagine thread number 2 going before the red one, which means that now you will have the 7 below the 4 in the stack. Now, if there is a third thread which is trying to read or to pop, it's not clear whether it will read the 4 or the 7. It's not given a priori. There is some non-deterministic aspect of the behavior of the system. And this is something which makes life difficult, because if you wish, we are going from the world of deterministic systems to the world of non-deterministic systems. And the non-determinism comes into the picture because you have concurrency, which means that you don't know the scheduling beforehand. You don't know which thread goes before which when you execute the system. So in this second scenario, thread 2 goes before thread 1. Yeah, so the question is, which one is the correct scenario? Which thread goes first? And this is a question mark. In fact, it's not clear. It's not even clear what it means to be correct in such a setting, as we will see later. This is interesting because the very basic notion of correctness is not clear due to the non-determinism that's introduced because of concurrency. Okay, so now, as I said, it's not easy to see what a correct, as we'll see, it will not be easy to see what a correct system is. It's even less obvious to guarantee correctness, what it means, how we guarantee correctness, and at the same time maintain efficiency. Because an important trade-off is that you design systems that work in the concurrent setting, which are, on the one hand, efficient, and we define some notions of efficiency later, but also correct in the sense that we will define later. So our aim in this course is to have efficiency and correctness. And by efficiency, you may have time efficiency, and which means that how much time it takes for the algorithm to solve an instance of the problem. So what this means is the following.